Let me share my screen. I hope it's visible. Okay, so very good afternoon, everyone, and thank you so much for joining. I'm Meghna Tail, Head of Marketing for Energy and Environment Group Field at HORIBA, India, and I'm very much delighted to welcome you all for this today's second session of EcoEdge webinar series. EcoEdge, Ecology plus Innovation. So the goal is to explore cutting-edge solutions that drive both industrial progress and environmental responsibility. But before we deep dive into the technical session, let me walk you through some quick insights about HORIBA, both globally and here in India. The HORIBA Group, a global analytical leader since 1953, serving the markets of energy and environment, bio and healthcare, materials and semiconductor. We are into R&D, manufacturing, sales, and services. Our head office is in Kyoto, Japan, and Atsushi Horiba-san being the current chairman and group CEO. Horiba India Technical Center, state-of-the-art facility, has become a demonstration base for emission measurement systems and advanced analytical instruments. Also, we have recently launched the hydrogen internal combustion engine testing facility at HITC Pune. Our major clients in India and SAARC nations. Now, I'm very much pleased to introduce our next two speakers who will enlighten us through the session today. Up first is Mr. Gaurav Bali, Chief Engineer, Functional Safety, and Mr. Simon Gresti, Manager, VRES. Together, they bring deep insight and experience from the world of functional safety. Let's listen in to what they have in store for us. I would now request Mr. Gaurav Bali to please take up further.
Thanks, Meghna. Okay, I'll just start with sharing my screen. Okay, that's coming through. Hi, everyone. So I'm Gaurav. As Meghna said, I'm one of the chief engineers for functional safety at HORIBA Myra. The last 15 odd years, I've kind of been in the low carbon domain, predominantly sort of vehicle lightweighting, functional safety, and system design. So I'll try and talk to you today about functional safety predominantly. So we'll start with what is functional safety? Why should we be doing it? How pervasive is the impact of doing it or potentially not doing it? Then we'll kind of do a little bit of a technical deep dive into some of the basic fundamentals of 26262, which is the leading standard for functional safety. Then we'll try and do a live walkthrough of an example so that you have a little bit of a technical takeaway from the session as well. After that, I'll hand over to Simon, who'll talk to you more about our presence, what services we offer, and how we can help your business. Towards the end, we'll be happy to take question and answers from around the table. So, what is functional safety? The strict definition or the key definition used in the industry is the absence of unreasonable risk due to hazards caused by malfunctioning behaviors of EE systems. Now, I know that's a mouthful, but the idea behind it is to highlight that it's unreasonable risk because risk can never be completely eliminated. The moment we step out of our houses, there is risk. Even within our house, there is risk. Breathing, there is risk. So it's the absence of unreasonable risk that we're trying to design against, caused by malfunctioning behavior. So what we're trying to highlight by that is that functional safety's realm or scope is about malfunctions or failures. So if the design is just poor, that's not within the scope of functional safety. That's a different standard, different discipline, called SOTIF, Safety of Intended Functionality. And the scope of 26262 is EE system. So we look at that in this slide a little bit more. So if you imagine the overall product safety as this blue circle, this includes everything from crash safety, from fire hazards, from shocks. And what we want to try and highlight is that there's a subset of that that's influenced by electrical and electronic systems. The blue set is perhaps things like a half shaft braking, right? There's no electronic or electrical interaction in that. So that is in the blue circle, but not in the purple. So it's outside the scope of 26262. Now, within this purple circle, which is all the factors associated with electronic and electrical systems, there is a subset which is because of malfunctions. As we said, there are poor design choices which could be made, and that's again outside the scope and covered by SOTIF. So functional safety really is a leading discipline, but a subset of your overall product safety. And that's important to understand before we jump in. So just to again recap, things like electric shock, if just a conductor is exposed, is poor design. That's by definition, by design, not being safe. That is not covered by functional safety. If there was a ECU or an electronic control system which exposed us to perhaps overheating of a component, which then caused fire, that would be within the scope. But a simple fire because of a short circuit, which is not influenced by an ECU or a control system, is again outside the scope. And similarly, there are other technologies and the hazards listed here, which are outside the scope. Now let's have a quick look at what the structure of the standard looks like. Many of you may have seen it, some of you may not have seen it. So 26262 edition 2 has 12 parts at the moment. The first part is the vocabulary, which equips you to understand the various terminologies that are used through the standard. Part 2 is sort of the overarching umbrella of management of functional safety. It involves things like the procedures, safety culture within the organization, the templates you might have to develop for your various parts. So it's about how you manage the overall functional safety. Then come parts 3 till 7. And this is where the more familiar engineering V cycle kicks in, right? So at the top of the V, we start at a concept phase. We move to the system level in part 4. Part 5 is hardware, part 6 is software, and part 7 comes back up towards commissioning and operation and decommissioning as well. Parts 8 till 11 are essentially supporting parts and some informative parts to basically better implement the principles of functional safety that we would have come across in the first few parts. And then part 12 is a new addition in 2018 to adapt what used to be just for passenger vehicles up to 3,500 kilos. Part 12 now adapts to 6262 for motorcycles as well. And what we want to show here with these little V's is that when you're developing hardware and software, it's important to acknowledge that you would do design as well as testing in hardware, in software. So you have these little V cycles going on within these parts as well. So it's the overarching V cycle and then little V cycles you might have to be doing. Now here is a question before we go to the next slide, just to see if you guys have been paying attention. So Meghna will put it on your screens, hopefully. And I'll give you a few seconds to read that and answer before moving on. Okay, so 26262 is significant effort. It's made of 826 pages. There are more than 4,000 clauses, subclauses, requirements, and recommendations. And these impact things all the way from your organization structure to reporting structures to design principles, the redundancy in the concepts of physics and electronics you might need to implement, all the way down to failure rates of components, hardware metrics that you have, to the number of cores in ECUs. And here is a quick look at the key artifacts you would need to produce, even for a relatively simple project. So the takeaway is that it is significant effort. So the question we need to ask ourselves is, why would we do this? What's the value proposition? So inherently, 26262, the way it's structured, lends itself to an accurate risk assessment, contextualized to your target application and your target market or your operational environment. So it gives you an accurate risk profile. And then the development integrity that it asks you to put in, the rigor, design rigor it asks you to put in, is directly linked to the risk profile we would have determined. So if your system is not very critical and you are following 26262, even by following 26262, you would not have to implement a lot of design rigor. Consequently, if you have a very high integrity system, you will have a lot of requirements to test, to develop, and validate. Beyond 2.6, it also implements a strong safety culture. It implements a safety-first thinking, not just in EE systems throughout the organization. It also lays down the foundation for adjacent disciplines like cybersecurity. The underpinnings of functional safety and cybersecurity are very, very similar. And the other key aspect is that in the future, you might have ADAS systems coming in, higher autonomy systems coming in. And what they will require is for the base development, like your powertrain, your brakes, your steering, all to have certain integrity of development. So by implementing 26262 early, you're future-proofing yourself for technologies that are yet to come. Now, how pervasive is the impact of implementing and, as I said, consequently not implementing, right? In a general design cycle, we start at a hardware level. We then move on to the software or the basic software of that ECU. Then we develop the application layer. And if I had to ask you where you think safety fits in, your answer will most likely be as an umbrella at the top, monitoring our whole system. And you would be right in the sense that you would have this overarching umbrella detecting your faults, reacting to them, putting your system in safe states, and doing that gracefully in a way that feels intuitive and safe to the driver. What is less obvious is that there is impact downstream as well of functional safety. So if you were to implement functional safety at the application layer or at a system level, you might need to consider things like redundancy in your communication channels. You might have an additional CAN channel to supply some critical signals. You may even consider distributing your functionality in a way that all your key functionality doesn't sit in one ECU because it would drive the integrity very high of that ECU. 2.6 may drive you to have memory partitioning. It may ask you to have a certain software architecture which lends itself well for you to have the kind of system level development that you want. And as we discussed early on, it also has governing principles for redundancy in hardware design, and it might even direct you down a path of the number of cores you need in a certain microcontroller. So it's not something you can tack on later at the end of your development cycle. It is something you have to embed at the start and in the very fabric of your development. So why are we doing this now? A little history lesson here. So back in 98, there was a standard called IEC 61508, which put really the foundations of functional safety or formalized the foundations of functional safety. 26262 has built upon that and expanded a little bit. The first edition came out in 2018. We are currently on edition 2, which came out in 2018. The first one came out in 2010. The third one is expected somewhere around 27 to 28. Now, where the industry is at right now is some of the initial leaders started to implement this within a year or two of it being released in 2010. And that was the time when the industry was understanding what functional safety is, how to interpret the standard and put it in their development, right? We're still not too late. If we implement now, we would still be amber, which is better than the tail enders. So now is still the time to get started, and perhaps we'll catch towards the tail end of the development. If you start today, you would probably have the edition 3 coming in, and you could update your design cycles to include principles of edition 3 as well. So it's a great time to start. Now, just a quick look at what the global status is. This is the picture from a few years ago. So important geographies like South America and India, back in the day, they had not acknowledged functional safety for the local market yet. For the US and China, they had activities underway, but they hadn't really adopted functional safety. It was really Europe, which was leading the charge, and Japan, which was kind of following close behind. Since then, we have had quite a bit of adoption or activities underway in these geographies as well. So South America and India have activities underway presently. The US and China have moved from activities underway to partial adoption. Japan
Gaurav,
has, yeah.
just a quick note. The slides I think were lagging a little bit. It didn't change this one. It just changed for me. I hope it's changed for everybody now. I think it was stuck at that timeline for part, edition 1, edition 2, edition 3. That slide was stuck. Okay, I think it's changed now, so it's all good.
So is this the map at the moment?
Yeah, right now it's showing the map.
Okay, and you can see my arrows that I'm drawing.
Yeah, that's what's
okay. So we're live. Okay. Thanks, Ash. Okay, so the aim really, you haven't missed much. The aim really is to say that the global picture for adoption has been changing. So as you see there, from ambers and reds, we have moved to blues, which is partial adoption, in greens. We still have a little bit of lag in the Indian market and the South American market, but that's to be expected. What we have seen that is encouraging is new geographies like Turkey, Saudi Arabia, Vietnam. Their developments, for the first time that they're developing, they are coming in with functional safety. They did not start their development cycles without it. Even new startups out of these geographies have been incorporating functional safety from the get-go. And the question we get often asked is, well, it's a standard, it's best practice, but what's the requirement for it, right? What's the legal requirement for it? And up until now, up until recently, it has been a standard. It has been best practice. But more lately, the UNEC regulations have started making very explicit references to 26262 or activities directed by or called on for by 26262. For example, Reg 79 has a direct reference to a HARA. Reg 152 has that as well. Reg 157 has explicit references to SOTIF, as well as the approving authority or the assessors to be well versed in ISO 26262. So it's making its way into the regulatory framework as well. Here's another question on your screen to see if you've been paying attention, and I'll give you a few seconds. Okay, so the next part of this seminar is we've introduced functional safety. The next part is to kind of give you a little bit of a technical slice of what it is like to do functional safety and what are the foundations of 26262. So it starts with a mix of the functional architecture and the primary functions of your system, and we iterate on them till we reach a state that we are happy in terms of the architecture and the primary functions. Once we have this, we treat them with a certain set of guide words. For example, if you have a function for providing acceleration, the guide words you might treat it with is undemanded acceleration, excessive acceleration, reversed acceleration. And that leads us to have certain hazards, which then we consider in the context of a scenario. And we'll look at an example, by the way, to make sense of all of this. Once we have this hazard in a certain environment, we then risk assess that sequence of events. We try and understand what criticality that sequence of events carry. So we look at the exposure of that, we look at the severity of that, and the controllability.
Gaurav, just a quick sort of interruption, sorry. The slides, I think, are lagging again. Some of other people are facing the same thing. Yeah.
Okay, I'll just go slower then. Are we at safety goals?
It's now showing the sort of life cycle, yeah. The malfunctions, hazards, operational situations, yeah, that one.
All the way to safety goals. Okay.
Yeah.
All right. So so just to kind of recap, we start with an architecture and functions, which is at this stage. Beyond that, we treat them against certain guide words. We come up with hazards, which could be of the nature of undemanded acceleration or excessive deceleration. We then risk assess that in a certain environment, and we write safety goals, which are really our top level safety requirements. The next step at that point is to try and understand what within our system can violate that top level safety requirement. So if we had to prevent excessive acceleration, we try and analyze what in our system can cause excessive acceleration. And that is the failure causes. Once we have identified those, we try and write some requirements and some safety strategies to address them. So really, you can look at this life cycle in three parts. The first is a set of inputs, which is covered by the item definition. The second is the problem space that is analyzed by the HORIBA, as well as the safety analyses like fault tree analysis or the more familiar FMEAs. And then final stage is the solution space, where we try and take all the failure causes we've identified and write requirements and come up with safety strategies to address them or mitigate them. So let's look at what the item definition looks like. Visually, this is what the document looks like. So it'll try and cover the operating modes and states of our system. It'll try and capture the scenarios in which our system operates. And this is very important for high autonomy features or ADAS features. You want to capture the operational design domain, which essentially says where your feature operates. If you have a traffic jam assist, does it operate on the highway? Does it operate inside a city only? Does it operate in rain? And so on. The next is what the intended target market is. Are there any legislative requirements and applicable standards in addition to 26262? And then what usage scenarios you consider. Carrying that on, it also gives you an opportunity to capture key assumptions. And even though we are going to do a full risk analysis just as the next step, it gives you an opportunity to capture the knowledge that exists from previous projects in way of known failure modes and hazards. And then finally, perhaps the most important aspects of the item definition are to capture an item boundary and come up with your core functions or primary functions. So let's look at that a little more in detail. This would be what a black box item boundary would look like in your item definition. So it essentially tries and captures the systems or ECUs that you take inputs from. And as your system, it captures what outputs and what functions you send to the rest of the vehicle in terms of the ECUs and systems you interact with. You can then also have a glass box view of this to capture the functional blocks that live within your item boundary. And then finally, you want to come up with a list of your key functions, core functions, or primary functions for your system. And this is what makes for the key input into your HORIBA. So the next thing that we look at is the hazard analysis and risk assessment. So this is the problem space, as we said. We've looked at the inputs. The problem space is the HORIBA. We break that down into two steps. The first is a functional failure analysis, So we look at what this is in a minute. And then the second step essentially is doing the risk assessment. Okay. So the FFA, the functional failure analysis, is taking our primary function, each of our primary functions, considering them against a certain set of guide words. So for every primary function, like request torque from the front motor control unit, we might consider a guide word undemanded. And what this would give you is if you have undemanded torque from the front motor control unit, you would end up with undemanded acceleration. So that is your hazard at the top. Now, what we want to do is consider this hazard in certain scenarios, right? So a scenario on your screen is our vehicle, ego vehicle, waiting at a T-junction. And one of the ways this can play out is there is cross traffic and the ego vehicle lunges forward because it had undemanded acceleration whilst we were waiting. And this leads to an accident. And we would need to analyze this as part of our risk assessment. So what the risk assessment considers, as we said briefly in the past, was it looks at the severity of this kind of sequence of events. It looks at the exposure of how often we would find ourselves in this scenario and the controllability that is available at our disposal in terms of the driver being able to brake, steer, or take any other actions. It also accounts for controllability of other road users. So in the accident we just saw, the ego vehicle's driver could have hit the brakes, as well as the driver of the cross traffic could have seen the ego vehicle lurching forward and tried to hit the brakes. So it takes the net controllability of all the actors in the scenario. So to start with, let's look at the interaction between severity and controllability. And this is a live example we'll walk through. But before that, a little bit of understanding of severity. It's essentially graded in a grade of criticality. So if there are no injuries, we call it S0, being the least critical because there are no injuries. Then comes S1, which is light injuries, and a greater than, it's always defined by a greater than 10% probability of certain type of injuries. So S1 is light injuries, greater than 10% probability of light injuries. S2 is greater than 10% probability of severe injuries, but survival is probable. S3 is greater than 10% probability of severe injuries, which are critical and likely fatal. So survival is improbable. So ranging from S1, no harm, to light injuries, survival probable to survival improbable is how we grade severity. Controllability has a similar set of gradations. C0 is your normal braking for the vehicle in front of you. C1 is something we consider almost everybody able to do. So greater than 99% of the average drivers are able to avoid harm. C2 is between 90 and 99%. And C3 is anything less than 90%. We don't take controllability credit for that. So as you can see, the bar.
Just a quick note, could you hold on to that controllability slide because the slides haven't changed. They're still showing severity at the moment.
Oh, okay.
Yeah.
Let me know when it changes.
Okay. Could you try switching slides a little bit, see if that, because it's still showing the severity on my side.
I am doing that.
Doesn't seem to be helping. It's okay. Yeah, now it's changed to controllability finally.
Okay,
go on.
Thanks. Sorry about that, guys. So yeah, controllability is graded in the same way as severity. Severity is S0 to S3. Controllability is C0 to C3. Now let's look at an example. So for undemanded deceleration, we were talking about acceleration so far. Let's look at undemanded deceleration. Here, there are different ways to do it. One way to do the HARA is purely qualitative. The other way is sometimes to augment a little bit of calculations and add that quantitative backing to the assessments we are making. So what we're trying to do here is basically have calculations of our ego vehicle. These are calculations of the vehicle behind us. These are calculations here of the delta between the two vehicles. This on the left is the distance between the ego vehicle and the vehicle behind. This is the speed difference between the ego vehicle and the vehicle behind. So visually, this is what it looks like. The red vehicle is our ego vehicle. The following gap that we assumed at the start is 2 seconds, which at 130 kilometers equates to a distance of 72 meters. So this would be our starting in this particular scenario. The hazard that we have considered is undemanded deceleration. And this is maximum deceleration of the vehicle. For most passenger cars, this is around 0.8 G. So what we want to understand is how the sequence of events play out. And because this is a severity calculation, we do not take any credit for the vehicle behind us being able to react to us having a decel fault and braking. So there is no deceleration expected from the vehicle behind us. And this is one of the key things. Severity is considered independently, then we tack on controllability and we consider them together. So without any controllability actions taken into account, this hazard would lead to a crash 4.3 seconds later with a closing speed of about 33.75 meters per second. What that equates to is about 120 kilometers per hour and 75 miles an hour. Carrying on the quantitative approach, we can look at a data set that's available. This is the NHTSA collision statistics from the US authority. And in this case, it is a straight accident. So we consider the head-on category. And in terms of the closing speed, because we had 75 miles an hour, we consider this third category, which is greater than 60 miles an hour. And what we end up with is a severity 3, S3, because in this scenario, based on the statistics that they had, more than 15% of accidents which were head-on with a closing speed of more than 60 miles an hour led to fatal injuries 15% of the time, which is more than the 10% threshold we have for S3. So therefore, if we were rating this in our HARA, we would have written decelerating up to 0.8 G with surrounding traffic. We would have put our rationale. We would have written a qualitative rationale based on the calculations we have done, and then rated that with the appropriate severity in our hazard analysis and risk assessment deliverable. So our severity is set at S3. What about controllability? So if we take the exact same scenario, now we start to bring in the reaction of the following vehicle. So what we try and do is a C1 hypothesis testing, which is to say 99 percentile of the people, what is the reaction time of 99% people? And based on, again, some statistics that we have, that comes to 1.35 seconds, with 0.3 seconds to press the brakes. In other words, we expect that the vehicle behind us would apply brakes 1.65 seconds later. So again, to visually play this out, we have the 2-second distance between us and the vehicle behind. Our vehicle experiences an undemanded deceleration event. The vehicle behind immediately is not able to react, but after some time passes, as we said, 1.65 seconds. So at t equals 1.65, we expect that the vehicle behind is applying some brakes. But based on research we've performed, most of the time people apply about 80% of the braking that is actually required in that scenario. So this is a fair assumption of how realistically things play out in the real world. And we try and do testing for that, right? So if we had 99 percentile people applying brakes 1.65 seconds later, does that prevent a collision or not? And what this graph here shows us is the distance between the two vehicles. So the moment it reaches 0, that means the two vehicles have made contact. So 99% of the people, their reaction time is not sufficient to avoid this collision. So let's try and test for C2. The threshold for that is 90% people, and the reaction time is a little bit faster. So instead of 1.65, we have 1.3 seconds before the brakes are applied. If we run the same calculation for that, what we find is that, in fact, the distance between the two vehicles does not become 0. They come to a stationary stop before coming in contact, and therefore we can conclude that 90% of the people would be able to avoid this sort of accident. So controllability, we could rate C2. Now, the third factor that's left is our exposure.
Gaurav, I'm really sorry. The slides seem to be lagging again. So could you maybe switch on? Yeah, just quickly, maybe on the last slide for controllability, we could.
Yeah. Gaurav, could you try switching off your camera?
Switching off the camera? Sure.
Yeah.
Okay, is that coming through?
Yeah, it's okay.
Yeah.
Okay. So what we've walked through so far is that severity we've set to S3. Controllability, based on the hypothesis testing we did, we've set to C2, because C1 required 99% people and their reaction time, which was not quick enough to prevent the collision. So we could not claim C1, we could claim C2. Now, the third factor that we have to determine is exposure. So exposure really is how often we would find ourselves in the operational scenario where this hazard could play out in the way we saw. So let's just look at the ratings first. So E0 is incredibly rare. This does not even have a quantified probability. E1 is any scenario that we might experience less than once a year. So if we are broken down by the side of the road, that is a E1 sort of an event, because you're not expected to break down regularly or more than once a year. E2 is few times a year for the great majority of drivers. And for a sense of duration, it is less than 1% of the time you're driving out on the road. So what you might experience less than 1% of the time, or frequency-wise, few times a year, we would rate E2. What you might experience more than once a month, so every few days, or on an average, less than 10% of the time you're driving, is E3. Now, the interesting part about exposure is, while severity and controllability had only 4 classes, exposure actually has 5 classes. So there is an E4 as well, which is almost every day something that is experienced by an average driver. So events like overtaking, events like waiting at a junction, events like hitting the brakes, these are daily occurrences. And in terms of the duration, anything that you experience for more than 10% of your drive cycle. So driving on the expressway or the motorway is a perfect example of E4. Which leads us to conclude that our particular example, where we were decelerating, is an E4 scenario, because it could happen on any highway or any high-speed road conditions. So we end up with an S3, C2, and E4 for this particular scenario of undemanded deceleration on a highway. All of this we are trying to rate so that we can get to what we call the automotive safety integrity level, ASIL. And this is the table available in 26262. So let's look at where we end up. With the S3, we are on the rightmost column. C2, we reduce that window to the middle. And then E4 brings us to acyl C. So this particular scenario, or hazardous event, as we call it, would have an integrity of acyl C. Now, just to recap, at the start of the session, we were trying to understand where we begin with functional safety. We looked at the fact that it's a combination of an item boundary and defining our functions. So we came up with an example function of request torque from the front motor control unit. We then put it across some malfunctions. If we were requesting braking torque and the malfunction was undemanded, the hazard we would end up with is undemanded deceleration. Then we took that hazard of undemanded deceleration and considered it in an operational scenario of everyday driving on a highway at about 100 to 150 kilometers per hour. Then we performed a risk assessment where we looked at the severity of that, the controllability of that, and the exposure of that to come up with the acyl rating.